you see actually then no class on Friday. And today we'll knock out the third of 4 chapters. That leaves one more chapter before your unit exam. And so we're going to need Monday, Wednesday to lecture. Okay? So Monday and Wednesday next week we'll hit chapter 13. And so that puts your unit exam on a Friday. Good, bad, or otherwise. It just is. That's the 31st. That must be Beggars Night? I don't know.
I think it's the 30th.
Is it the Thursday? Okay. So a couple of review sessions. It might seem kind of strange, but I'm going to be in my office anyway, so if there are any takers that Monday morning at 9:30, the thing about it is, it will seem strange is we'll have a whole chapter that you guys will have not yet seen. But I like to have a morning and an afternoon session, and I don't like them to be on the same day or it will drive me nuts. So we're going to have a review session after class-ish on Wednesday, next Wednesday. Any questions about that? Okay. Cool. So, yeah, and then this is just nothing new. Actually, this is the same slide I showed on Monday. And, of course, the morning lab has come and gone. We had one person show up, which is kind of normal. So I was glad that she showed up. And it was beautiful. So, but what we do have still yet, I don't know if Thursday morning it will or not, but Orionids have been going on, kind of peaking. I saw some of those yesterday morning. And then, like you were saying, the partial solar eclipse. And I say you can make your own pinhole viewer for lab credit, write it up. Sometimes students say, well, what do you want? Well, usually for a lab write-up, I just want you to describe what you did or what you saw. Okay? That would be great. Clear skies, though. And then next Wednesday, we're opening up the observatory in the evening, about 6:30. So it should be fun. I like these anyway. And then a week from Thursday, it's the Sun Lab here, only if the skies are clear. Notice we have 2 dates for our labs. This is the first try at our Sun Lab. So if it's cloudy, then we go to our secondary date, which is about a week later for the sun. Yeah.
Is the 6:30 one, is that the second one or the first one?
That is the second one. So it will go regardless. Yeah, that's our second try at that, I think. Yeah.
Tomorrow's my kid's spectacular at school, so I won't be able to go.
Yeah, and that's a week from Thursday. It's not tomorrow. So, yeah. Woody Observatory, it's the...
So I don't remember if it's this Thursday or next Thursday, so...
Okay, all right. Yeah.
It's next Thursday, I won't be able to go.
Okay. The one thing about it is, most teachers are very introspective, good, bad, or otherwise. And I do try to make it fair. So there are generally a lot of different opportunities. If you can't make it to Whitty, it's like, I'm not going to drive that far. Well, there's other things you can do. Yeah, I know. Yeah, you could. Kids will love it. So we need to finish up this chapter. But stars are awesome. Stars are exciting. Stars make our constellations. But stars kind of come and go. And actually, this chapter and the next chapter we're kind of talking about, and actually the next unit we'll be talking about the deaths of stars, ultimately. So they do blink out eventually. But when we talk about characteristics of stars, in Monday's lecture we talked about the brightness of a star, what it looks like, its apparent brightness, and we also talked about its luminosity, what it's really energy, what it's really pumping out. And we kind of classified stars generally relative to the luminosity of the sun. We also need to talk about masses of stars. And what you're going to see here in a minute is we're going to kind of characterize the masses of those stars relative to the mass of our sun, because it's all about us, right? Okay. So in order to get to the masses of stars, we get to that using Newton's law of motion, how gravity affects the motion of stars. And the gravity I'm talking about is basically the influence of a companion star. So it's wonderful. Most stars up there are actually in pairs. Okay, we call that a binary star system. Okay, and they're doing this dance, and we watch the dance, and we can get to their masses. So I'm going to actually kind of show you the equation, Newton's equation, to how do you get to the masses of the stars depending upon their dance. And I'm not going to make you apply it. I just want you to see the equation. So, different types of pairs of stars. Now, one of the things that I think to emphasize is visual binary star system, eclipsing pair, spectroscopic pair. they are not different with regard to the stars. They are only different with regard to how we know there are two stars there. That's it. A visual binary, we can see them. Eclipsing binary, we see them eclipse each other. A spectroscopic binary, I'm going to show you this, we basically use the Doppler effect. Okay, so it's how we find that, not necessarily, but they're not any different than each other. So most stars are not by themselves. In fact, some stars are more than just two. They're actually a set of three or a set of four. The other thing up there is that some of my favorite things to look at through the telescope, the pairs of stars, the binary stars, actually are just optical binaries. Okay, they aren't really doing a dance like this. They just happen to be kind of lined up in our field of view like that. So they're pretty to look at, but you basically can't get to their masses because they're not doing a dance because they're not near each other. Okay. All right. So visual binaries, you can see them. Okay, we can see two stars there. And you can kind of see through this course of slides kind of a dance that they're doing. Okay, so scientists can look at this dance and then understand the masses of these two stars. This is actually Sirius. The star Sirius is just apparent brightness, but the brightest star in the night sky. Seriously. I want to say the northern hemisphere, but probably in both. Okay, so there's a visual binary. You get to see them both. The eclipsing binary and the spectroscopic binary are a little more elusive. You have to do a little bit of science magic to see them. So the eclipsing binary, what you do is basically, in this pair of stars, these are stars. The blue one isn't a planet. The blue one is another star. Okay, so you have a blue star and an orange star. And they're doing a dance. In this case, it happens to look like the orange star is kind of in what we call the center of mass. So it kind of looks like the blue star is orbiting the orange star, which is possible because it's so big. The orange star is so big. So basically then, if we were to have a light meter here on Earth, looking at that pair of stars that we can't necessarily see two, it's not a visual binary, what we can do, though, is see a difference in the amount of light that they're sending us. So here we see basically if we're not necessarily in full view of we can't necessarily resolve two stars, but if there are two stars there and they're both sending light our way, we have the maximum amount of light coming from those pair. As the blue one goes in front of the red one, notice basically it takes a little bit, this circle, it takes that much light away from the red one that was trying to send light to us. So literally we see the light dip down. And if we talk about eclipses, right, we're going to have hopefully, well, it will occur whether we see it or not, but an eclipse of the sun as the moon goes in front of the sun here tomorrow, you know, a certain amount of light is blocked out, okay. Then, of course, the blue star continues its orbit, and you can see when it gets to the side then, when they're both sending light to the Earth, we're both at max. And then as the blue star skirts around behind the orange star, we again see an eclipsing sort of situation. In this case, the disk of the blue star is entirely eclipsed by the disk of the orange star to us. So literally, we would see it, our light from those pair of stars would go down. Okay, so it's an eclipsing binary. And we just kind of see this signal. Okay. Now notice a few things, though. This has to be kind of like edge on, right? I mean, it won't work if it's like this, right? Okay. So, spectroscopic binaries, okay? So we have visual binaries, eclipsing binaries, and spectroscopic binaries. I mentioned this uses the Doppler effect. And so we're looking at the same sort of situation where you have one star that actually is lying in the center of the dance position and the blue star, you know, orbiting the large star. So can you see where in position B up there, okay, as it swings this way in its orbit, okay, it swings this way, it's actually coming towards us. And we talked about if something's emitting light like this and it's coming towards us, it's going to actually, its light's going to be squished together and the wavelength's going to be shortened. We call that a blue shift. Okay, then when it skirts around the backside, it's going away from us and we will see a red shift. So those black tick marks are absorption lines from probably hydrogen. Okay, when we compare the lines these absorption lines to a library sample, we're going to see that these are longer, okay, and these are shorter. So it's kind of fun. We have this kind of blue shift, red shift. I should say in between, just to kind of remind you of something we talked about before, we talked about proper motion. Let me choose a different color. Okay, so right here, actually, as the blue star is moving sideways relative to us, that's proper motion, and there's no shift at all. Something we talked about before. Oops, darn it. Okay, this is a blue shift, this is a red shift. And the top and the bottom are what we call radial motion. So here's the equation that you don't have to use, right? So this basically, I've been talking about the dance. That dance has a time, we call its period. That dance also has kind of a distance between kind of the center of motion, or I guess I should say the partners have an average separation. That's the A term. Okay, and of course the pi is a constant. G is a constant. We talked about that back in chapter 4. G is the gravitational constant. And these big M1 and big M2 are the masses of those stars that are doing the dance. Okay. So if we're not careful, if you're kind of familiar with kind of looking at a relationship like this, you're like, well, we don't know the masses, okay, and we need to study the stars and hopefully find out the periods and hopefully find out the average separation. So that kind of emphasizes this. If you're only going to have one, what we call one equation, like you saw back there, you can only have one unknown in there. And so we need to know at least two of these three to solve for the third. And usually what we're solving for is the mass. So, another field, looking at those pretty stars again. The assortment of colors, we kind of talked about that on Monday. We said that the red stars, remember, are the cooler surface temperatures, and the blue stars are the hottest surface temperatures, kind of like those radiation curves. Of course, humans are down here. We basically emit no energy with regard to, or no energy in the light part of the electromagnetic spectrum. But now, using the dances, using pairs of stars, watching how they behave, orbit each other, we can come up with the masses of stars. And generally, we have a range. We have an upper range, the mass of the star, about 100 solar masses. And we have the smallest, the least massive star, and we'll talk more about this. I think it's still in this unit. We'll talk about why you can't have anything smaller than about 0.08 times the mass of our sun. It just doesn't get off the ground. Okay, so that's kind of the range we're looking at. Alrighty. So, Hertzsprung-Russell diagram. We'll be take a little bit of time here with Hertzsprung-Russell diagrams. It's kind of cool because if you track this down, it's a way of looking at stars, and it's a scatter plot. In physical science, or I imagine in all science, a lot of times what we'll do is we'll look at, we'll take two characteristics of a population, in this case population of stars, two characteristics, and we'll throw them up on a plot. And we'll have something for the Y and something for the X, and we'll look for patterns. And it's amazing that these two scientists, about the same time, in different countries, did the same thing. And they came up with some patterns with regard to stars. Okay, Hertzsprung-Russell diagrams. And the two things that they plotted were luminosities, we're going to see on the y-axis, luminosities, how bright it is, not apparent brightness, but luminosity, okay, versus temperature along the x-axis. But there's a catch with regard to temperature. So this is an HR diagram. I'm not sure I really like kind of the black background. So they aren't really dots necessarily, but those orbs each represent a different star. Okay, so they're throwing up the stars, an assortment of stars, and you can find our sun on here. Where is our sun? There it is. I'll change color. Okay, so here's our sun. Okay, and those are just different stars. So like I said, now HR diagrams are kind of here to stay. You're going to want to familiarize yourself with them. But luminosity is the amount of energy they're pumping out. So the way luminosity goes is we have increasing luminosity like that. Makes sense, you know. And it's relative to the sun. Along the x-axis, we have temperature, but here's the problem. It's not really a problem. But do you see where this says increasing temperature over here on the left? So temperature increases kind of backwards to what we're used to. So we have the hottest temperature over here starting out at the origin-ish, right? Okay, so hot temperatures, cooler temperatures. So one of the important things that we covered in lecture on Monday was those 7 spectral types. O, be a fine guy or girl, kiss me. Okay? So there they are. 7 spectral types. O, be a fine guy or girl, kiss me. Okay? And it makes sense because we already talked about that. One of the things you're going to want to put on your note card for your unit exam is the 7 spectral types. I want to say 7 dwarfs, right? But 7 spectral types. So superimposed with those 7 spectral types are the surface temperatures. Remember that the core temperatures are a lot hotter than that. All right, so here we go. So patterns, and I'll go ahead and kind of start you thinking about the HR diagram and patterns. There is a very important type, or yeah, I'll say type. It's not really a type. There's a very important group of stars that are classified as main sequence stars. It's not a type, it's a stage in their life. Main sequence is a stage in the life of a star. It's kind of like middle age or young adult, okay? Main sequence stage. The other stages on here, I'll go ahead and highlight them. It kind of depends upon, a little bit depends upon mass, and a little bit depends upon age. But those 3 things I circled, the giants, the supergiants, and the white dwarfs, you can think of those as after main sequence because they are. Okay. But both Hertzsprung and Russell did this scatter plot. And they're like, dude, we see some kind of clustering here. We see some groups here. So yay for them. So just to kind of emphasize the x and y axis, here I added temperature increases this way, which is kind of strange. Luminosity increases along the y-axis as you go up, which is normal. The other thing I want to emphasize is that we can also, along the y-axis, put in addition to luminosity, the amount of energy a star is really pumping out, we can also put that type of brightness called absolute magnitude. Because we talked in Monday how absolute magnitude is basically putting all of the stars on the same finish line. It just has to be 10 parsecs from the Earth. And really looking at how bright they are. Absolute magnitude. So that is lock and step with luminosity. Okay. So I don't know if you guys needed that last one. So of course down here I already kind of talked about, one of the things we talked about in the previous lecture, those nice ladies. Looked at all those little fingerprints from the stars and kind of put them in 7 piles. All right. I don't think I'm necessarily gonna do this. This basically is what Hertzsprung and Russell took a blank graph. And they knew they wanted luminosity, increasing luminosity along the y-axis, and then they knew what they wanted, decreasing temperature along the x-axis, and put their stars up there. As kind of like, those are what we call ordered pairs, right, of information for each star. So it's kind of cool. Well, first off, so main sequence, I told you that is actually like this. I mean, it's like, stars spend most of their time as main sequence stars. The other cool thing, and we'll be talking about this yet in this chapter, is can you kind of see the size of the orb? The size of the orb is actually, remember the orbs of the stars. The size of the orb is an indication of how massive the star is. Okay, so we'll be talking more about that. So all of these stars are in their main sequence, and they have something in common with regard to how they're creating energy in their cores. But these are the least massive, and I have a slide to emphasize this. but these are least massive, but they have to be at least, what, 0.08 solar masses, and these are most massive. And it's kind of cool. I mean, we got the whole mass thing going, we got the whole color thing going. The least massive ones as main sequence are red. The most massive ones as main sequence are blue or white. Just a beautiful thing. So if we just kind of cluster these two, both the giants and supergiants, and if we kind of look at them relative to the main star, if it's in its main sequence stage, can you see where two things, basically they go up in luminosity, okay, so they are higher luminosity, but in general, I don't know if you can see this here, they are cooler. They're more luminous, but they're cooler. Which is kind of interesting as they age. You've probably heard the rumor that our sun is actually going to go into a giant stage I might have said this the other day, some 5 billion years from now, it's going to leave its main sequence stage. And it's actually going to move on the HR diagram. Okay, it's going to enlarge. Okay, so actually, the fact that these things become more luminous is basically a function of them enlarging. As they enlarge, basically they have more surface area. Okay, so they're enlarging, but it's going to become cooler. So you're like, hey, so things on the Earth might cool down? Well, not really, because basically the diameter of the Earth, or excuse me, the diameter of the sun itself is going to expand to, I think it's beyond Mars. So you're like, yeah. Future generations really need to come up with some idea here. Okay. So those two, we'll be talking more about why does something get larger and more luminous as it ages. And this is just like totally adorable. And to go ahead and finish the story about our sun, of course our sun is right here, about 5, did I say billion? Yeah, that was right. 5 billion years from now, it's going to go up here, and it's probably going to wiggle a little bit, okay? But eventually our sun is going to end up down here as a white dwarf. Okay, so sometimes I call this, and if you watch videos on this, like a bit of documentaries, they often call this a retired star. Retirement is a good thing. Okay. So we have the 7 spectral types, O, B, A, F, G, K, and M. Okay. 7 spectral types. And then kind of superimposed on this, we have something called luminosity classes. And I usually don't get down too much into the nitty-gritty, but hopefully you can see some of these things from an HR diagram. You see main sequence as a luminosity class. Okay, you see the giants as a luminosity class. So oftentimes when you'll see somebody point to a star or you'll read something about a star, it will tell you what spectral type it is. You know, where G is the spectral type of the sun. I think I kind of mumbled or mentioned, actually not just the 7 spectral types, but the 7 spectral types are further subdivided with a number, but don't worry about that this semester. So G2 is us. And then we are luminosity class, Roman numeral 5, which of course is main sequence. So that's how that goes. Some fun stars. I told you Sirius is the brightest star in the nighttime sky. It's not necessarily the hottest star, though, is it? It's an A-type, so O-B-A. It's like the 3rd from the hottest. And notice it is also main sequence. So Proxima Centauri, it is an M spectral type, which is cool, right? It's the coolest type. And it's also a main sequence. Betelgeuse, okay, the fact that it is luminosity class Roman numeral 1 means it's what? A supergiant. Okay, so more HR diagrams. So we said, and this is the same HR diagram, same set of stars. I think these are kind of random stars with names that you might recognize, like the sun and all that. Here in a minute, we're going to take a set of stars that really have something in common. They were basically born about the same time because they're a cluster of stars. And we're going to put them on an HR diagram. These are kind of random. So, of course, you see temperature along the x-axis. Color kind of goes along with what we talked about Monday. The M-type are red. Okay, the O-type are blue. Spectral type, of course, that's the O be a fine guy, kiss me. Luminosity along the y-axis. The last thing actually is kind of superimposed on here, and I'll kind of highlight what this radius. I don't know if you can see this, but this says 0.001 solar radii, 10 to the negative third, or 0.001. The way this works is as you go up with regard to the diagonal, you get larger radii. Okay, so this is the largest radius up here. Okay. So you can chant it quietly to yourself if you want. And in your unit exam, some semesters I actually give you an HR diagram, but it didn't go over real well. And I ask you questions like this. So it says, which is the hottest? So of course, hot, we must be looking along the x-axis, right? So we're basically looking at something, remember the hottest must be over here. So are you thinking A? That's right. Which is the most luminous? So we're then looking at the y-axis. And of course, luminosity increases as you go up. So just barely, it's close, B and C, isn't it? But I'm kind of thinking C. Of these, which are lying on, and you're going to hear me call it the diagonal. So this is very important diagonal. And it's not a pure diagonal. It kind of has a little bit of a curve here. And I've kind of seen it with a kind of a curve up there before. Maybe you're thinking of a titration curve. Okay, but it's not just an entirely straight line. That's a very important way to look at a star. We know those stars have something very important in common. They're in their stage we call main sequence stage. Of course, that would be D, right? See, now you're like, well, why don't you put that on the test? Well, I don't know. Not going to happen this semester. The last one, and like I said, is kind of a subtle thing. It's probably hard for you guys to read these kind of lines superimposed on this HR diagram. But they increase as you go up. So, of course, C has the largest radii of all those stars. Okay. So main sequence stars. Most stars are in this stage of their life. And I don't think it's a hard thing to understand when we start to understand how stars age. All stars go through, well, not all stars, because sometimes there's a little bit of difference in how they end their lives, but all stars kind of start their lives the same. And all stars, when you look at how their life is divided up, this is the largest part. So that's why most stars are this type. So main sequence stars that are hot are blue. Main sequence stars that are low mass are red and are cooler. Oops, sorry. So I think these are kind of repeating myself, but that's okay. So I would probably, in your note card, put an HR diagram on your note card and generally know what it means. Okay. So this, and maybe a few slides were also, and I've been talking about mass, and I like how this slide kind of, the size of the star is trying to kind of give you an indication of mass. More and more massive stars as you get the larger kind of up there. But just related to the mass of a star, as it's just related to it's a main sequence star. Okay, the more massive it is, the higher the luminosity and the hotter the temperature. The less massive, the lower the luminosity and the cooler it is. So something that we talked about in the chapter on the sun was this equilibrium. And I think that you guys is it this chapter? Must be, or Yeah, on the chapter on the sun, you guys answered, talked about, when we talk about the equilibrium of our sun, what are we talking about? And basically we're talking about gravity pulling in, okay, and the sun has nuclear fusion going on in its core, you know, the hydrogen to helium and energy, okay, that's pushing out. So that's what kind of this balance is talking about. So this is kind of a smaller star, okay, and this is kind of a larger star. Okay, so from left to right, we have smaller star, larger star. So the smaller star, actually, the red line must be what? Gravity, right? And if it's an equilibrium, I guess the way to emphasize that is I better show an outward pressure from that star having nuclear fusion in its core. Let's pick on purple. Okay, so this is, because it didn't look balanced before. There's the balance. So, but the deal with these more massive stars is that they must have the length of that arrow going out is showing you how much energy it's pumping out, how much energy it must be creating in its core. Okay, so basically these larger ones are creating more energy in core. Also related to creating more energy in core, and I think that's what this slide is emphasizing, is actually this is even more dense than its smaller counterpart. Why? Because it's larger. Okay? And that would be the red arrows, kind of gravity kicking in. So basically what you're going to see, and it's kind of a fun thing, I guess, is that these massive stars over here, they run through their fuel faster. Because they are pumping out the energy. So it feels a little bit contradictory. A star that starts out with, oh my gosh, a lot of mass, it runs through it a lot faster. So honestly, we're going to see if it runs through its fuel faster, it actually has a shorter life. Sad face. So what starts out is, it looks like it could go forever because it's got like 10 billion tons of fuel. Okay? It doesn't. It has a shorter life. It's neat because these M-class stars, these M spectral type stars, they have been around ever since. They have been around. Some of these little babies, this is not babies, they're like main sequence stars. They just keep pumping and pumping. They've been around ever since the Big Bang. It is totally amazing. So to kind of take a look at what we've been talking about in this chapter, we said the energy that a star is pumping out with regard to relative to the sun kind of has a range. Okay. And now to kind of superimpose on that range of having a low luminosity and a high luminosity, we can go ahead and say with regard to mass, that's the low mass stars and the high mass stars. With regard to temperature, now this would be surface temperatures. Okay, the surface temperatures run about 3,000 Kelvin to 50,000 Kelvin. Remember, sun's about 6,000 Kelvin. And again, to superimpose, of course, on the cooler end of the stars, we have those less massive stars. And in the hotter end of the stars, we have the more massive stars. Okay. And just to kind of remind you that we ultimately get to the massive stars. I'm trying to think, is there other ways to get to a massive star? I think the only way I've heard is basically observing its motion, okay, as it has a companion star. So we kind of have this range up here, and we'll talk about why stars that are less massive than 0.08 solar masses don't make it. Stars that are more massive than 100 times the mass of our sun, they just don't settle down. All right. So we're going to look at how long do these stars, and we're going to talk in terms of being a main sequence star. I think that's what I want to say. Lifetime, I'm going to add as a main sequence star. And we'll be talking more about this, I think, in the next chapter. But the thing that makes it a main sequence star is that it is basically, in its core, it is fusing hydrogen. That's it. That's it. And if you remember our discussion of what our sun's doing right now, we said in its core, it's fusing hydrogen. And that's what makes it a main sequence star. So yeah, our sun started about 4.6 billion years ago, and it's got about 5 billion years left as a main sequence star. Well, let's look at something that's more massive than our sun, specifically 10 times the mass of our sun, and let's look at how long it's going to live. So like I said, the more massive the star, the faster its fusion rate in its core, and the faster it's going to go through its stuff. So even though it has a lot more stuff, it's going to go through it faster, so it's going to live a lot shorter life. Okay, so instead of 10 billion years, it's 10, million years. Dude. Well, we got the other end going on too. Let's take something that is a tenth the mass of our sun, and let's see how long it lives. So it should live longer, right? So instead of 10 billion, it lives 100 billion years. It's kind of fun as we look for planets that we might move to, because we moved to another planet. The characteristics of the star that planet is orbiting is important too. They talk about these Goldilocks zones. So if it's a less massive star, it's a cooler star. So actually our Goldilocks zone is going to have to be closer to that star. Okay, so those are all things to consider. So here we have some stars. And again, kind of the bigger the star, it's trying just to indicate mass. And you can see with regard to how long they're going to live, here we have Proxima Centauri, an M spectral type. That's the OB fine guy kiss me. That is actually the least massive and the coolest. Okay, it's going to live 1 with 1 comma and then 4 sets of 3 zeros. So it's because it's 10 raised to the 12th power. And then Spica is only going to live 1 with 7 zeros behind it. So I hope you're kind of getting the idea. So yeah, the next chapter will go into a little more specifics. What are those giants and supergiants and white dwarfs? But I already told you they are stars that are no longer main sequence stars. They have left the main sequence. Elvis has left the building. Okay, and if they left the main sequence, what characterizes stars as main sequence is that they're fusing hydrogen in their cores. They must not be fusing hydrogen in their cores. Okay. So up there in the HR diagram, kind of the upper right, okay, we said that was more luminous and cooler. Giants and supergiants. And then those white dwarfs, which is what our sun will be, and we didn't talk about this, but they are kind of, I'd maybe classify them as lower left on an HR diagram. So let's see, lower on the y-axis means less luminous, and to the left must be, isn't that weird, hot? That's what white dwarfs are. I think we're okay with all of that. Oh, yeah. So this poster has been up on the bulletin board for a while now. At the beginning of the semester, I kind of talked about objects in the nighttime sky. One way to talk about different objects is the Messier catalog. Messier is French. And so some of the cool objects to look at in the nighttime sky are actually clusters of stars. And there's 2 types of clusters of stars. I saw this one yesterday morning. This is actually, it's got a few names. This is the Seven Sisters. It's also called the Pleiades. I can never spell that. Pleiades. It's probably really butchered. But the other thing is on the Messier, it is it 57 or 45? It is Messier object number 45, which is the least romantic but the easiest one to put in your go-to scope. Okay, so it's weird because, yeah, they call it the Seven Sisters, but it doesn't look like a seven sister. I mean, it does look like more than 7 stars, doesn't it? And we're going to look at them all kind of on an HR diagram here in a minute. So this is an open cluster. It's an example of an open cluster. And these stars were all born about the same time. Okay, they were born in the same, I love this term, stellar nursery. Isn't that just adorable? Okay. Sometimes, I guess one more thing, not related to the science, but related to what they look like. Sometimes students will say, Mrs. Snipes, what is that little dipper? And it does, if you use binoculars, it looks like a little dipper. I don't know if you can tell it here. But you're like, really? Okay, so that's one type of cool celestial object. This is also a type of cool celestial object. It's another group of stars, but can you see where they aren't open? They are actually globed together, and actually we call this a globular cluster. Again, they were all born about the same time, and these in general are old stars. These are the old guys. Okay, so these are old stars. These are very pretty too. Globular cluster of stars. So I said that instead of just kind of having a random assortment of stars to put on an HR diagram like we've looked at, what makes more sense is to put on an HR diagram kind of a set of stars like this that have something in common. So the things that open clusters and globular cluster stars have in common is they were born about the same time. Okay, so let's go ahead and see if this plays for us. So one of the things we just talked about is that the more mass of the star, it's not going to live longer. You're like, dude, you're shining too fast. Okay, so the more mass of the star, the faster it's going to blink out. But honestly, instead of blinking out, it's going to, what we say, leave the main sequence and go to kind of a giant red giant. And we'll talk in the next unit where a lot of times they blow up, right? So what this animation does is to kind of emphasize that. So if we start it going, you know, these were all born about the same time. This is a cluster of stars. Okay, so you see how that goes? The blue ones go first, then followed by the next least massive, you know, getting lower and lower mass. Red ones are still there. So if we were to take a cluster of stars all born about the same time and put them on an HR diagram, then we would have kind of an interesting sort of thing that we could look at. So there's how you spell Pleiades. See what I mean? It's like, really? What does that mean? Okay. So there actually is more than 7 stars. Okay, those are the Pleiades all put on the same HR diagram. And notice what scientists, or what you might notice, is that they are missing these guys. They don't have any high mass stars. Why? Because they left the building. They actually left the HR diagram. These peeled off first, and then these, and then these. And actually, these are getting ready to peel off. We call that the turn-off point. Okay? These are solid. Okay, these will be down here. These will be the last to go. Okay, so low mass last to go, high mass first to go. All born about the same time. So that kind of peel-off point is important. It gives us a sense for how long that cluster, whether it's an open cluster or globular cluster, how long it's been around. So here you see the Pleiades still here. They're kind of your blue triangles. And then you'll see a few other clusters. Okay, we have a cluster in purple, a cluster in blue X's, and a cluster in yellow squares. So can you see where the one with the, oh, I guess we have, yeah, that's right. So the one with the, trying to see, what is this one? Anyway, can you see where if you have a turn-off point, the farther you have a turn-off point near the low mass stars, the older your cluster of stars are. So as I circle them, I'm going to circle them from oldest to youngest. So there's that one, and then we get younger, and then we get younger, and then we get younger. Our turn-off point is higher and higher and higher. Okay? So So down there, where there is a turnoff point, it's telling you how old that cluster of stars is. Taking the data and kind of putting the data into a line instead of the dots. All right. So last slide. And I was kind of in a hurry, so I was looking at this, and I'm like, just to emphasize that the lower the turnoff point, the older the cluster of stars. All right? Very good. Well, have a great weekend.